Right, so we'll begin. We are delighted to have Girish from the University of Western Australia, who will tell us about how to deconstruct aggregate fluctuations. So, Girish, over to you.
Thanks a lot, Kanishk. And first of all, thanks for inviting me. And today I'll be talking about this paper by Damien Lenzo, a brilliant PhD student of mine who's probably also on the call. And we're working on this paper on, I think, since the past 2 years or so. But yes, please, give us as many comments as you can, and feel free to interrupt me if something is not clear, because clearly we have been staring at this stuff for far too long. So it'd be good to get comments. All right, so let's get started. So, well, to begin with, I think it's we kind of start from the point where you look at these recent macro models, especially production network models, and you see a clear consensus that microeconomic shocks matter, right? So if you think about Lucas, the idea was that microeconomic shocks shouldn't matter. And if you have a large number of firms or production units in an economy, then small shocks should average out at the rate of 1 by root n. But this literature essentially challenges that idea and says, no, hold on. The production network is kind of, it's a complicated web, and in the way firms are linked to each other. And due to asymmetries, small microeconomic shocks can blow up and cause aggregate fluctuations. And a seminal paper in this literature is by Haltom, 1978. This was a review of economic studies back then. And what he's saying is that he's giving a very general model. And he's saying you don't essentially need to worry about what the network structure is, how firms are or sectors are connected to each other. You don't need to worry about that. You don't need to worry about how a shock to one sector will kind of affect other sectors and probably affect it back. All you need to understand the macro effect of microeconomic shock is the sector's sales as a share of GDP. So as long as you have the sales share of a sector or any production unit, you can understand how a productivity shock will affect the aggregate economic activity, right? That's a very important result, because it's kind of a network irrelevance result. You don't need networks if you're working with efficient economies and Haltom's theorem. A caveat: I'll be interchangeably using sales share as Domar weight, which is the same stuff. Okay. Now, what is the problem here? I think the key problem is that while we know now that microeconomic shocks do have consequential effect on the aggregate economy, what we still don't understand is what linkages in this complex web of production network are important and really crucial in amplifying shocks, right? We still don't have that understanding, precisely because of the complexity with which these links are made and the way shocks propagate. So that is where this paper contributes. It contributes to understanding how and which linkages are important for aggregate fluctuations. Okay. So let me give you a few examples to kind of illustrate what we're talking about. So one example is network spillovers. This is one of the applications that we do. And I think it's very intuitive when you look at it. So if you go by Haltom's theorem, right, what it basically means is that if you think about Walmart and electricity production in the US, both have sales share of roughly 4% of the US GDP, right? So technically speaking, and to a first order, a large negative shock to both these sectors will have the same effect on GDP. That's not me speaking, that's Haltom. So this is true. If you want to understand what the aggregate effect is to a shock to Walmart or electricity production, they're going to be the same simply because of the same sales share. But the key point is that a decline in electricity production will affect economic activity mostly by affecting other sectors, right? And we call this aspect network spillovers, right? While a shock to Walmart will affect GDP by mostly affecting final consumption, correct? And that is what we call as what is known as the direct effect. So the key question is, how do we disentangle network spillovers with direct effects, right? Now you may ask, why do network spillovers matter? As long as I know what's the aggregate effect of a microeconomic shock, that is all I care about.
So Girish, I have a small clarificatory type question.
Go
So
ahead,
you do not have any networking kind of issue on the consumer side, right? It is entirely on the production side, right?
What do you mean by network from the consumption side?
Well, the consumers can well be in network, right? Well, suppose a particular community is like consuming something, and that has some effects on other communities.
So, okay, let me simplify, and I'll show you. The structure is pretty straightforward. We have factors of production right at the top, right? Then we have bunch of sectors, say whatever n sectors, that use these factors of production and intermediate goods to produce their output. And then finally you have the household that consumes output from these sectors of production. So the household would consume all of these goods and services in different ways. Does that answer your question?
Okay.
But I'll show that figure later down the line. So the household, you have a consumer, and the consumer consumes all goods and services, but in different ways based on their consumption aggregator.
Okay, thanks.
Yeah, I also have a question, Girish. So when you with these aggregate productivity shocks, what is going on with aggregate demand in the background? Is it, the consensus view is that demand shocks won't really affect aggregate productivity, right?
Yeah.
But in the data, you see that aggregate productivity moves with aggregate demand. So so in terms of your previous example, is that what is driving these larger effects? Apart from the shock being propagated over the network, is it also being driven by changes in demand as well?
Yes, so you can incorporate demand effects as well. But when we're thinking about productivity shocks, specifically micro productivity shocks, what we are assuming are, so to speak, these are supply shocks. These are supply shocks, but they can have demand effects clearly, and as a consequence, it can affect the aggregate output produced by the sector that is hit with that shock. But more importantly, it can also affect the output produced by other sectors.
So Bakai and Fari have a bunch of papers in this area, right? So you're citing this 2019 paper, but there I know there's more stuff after this. Do you know what the difference in these papers are for this?
Yeah, no, they have a bunch of paper, and in fact there's a big and growing literature, and I'll get to that. The key aspect, obviously, of the growing literature on networks is that you obviously have one set of literature that talks about efficient networks, and then the second bit is on inefficient networks, and you think about distortions and wedges. I'll come to that, and I'll also explain how we come in.
Okay.
Okay, so where was I? Yeah, so the question then is, why do network spillovers matter? If you know the aggregate effect, then why does it matter? So first of all, it matters for industrial policy, right? So it is important for policymakers to, for example, understand how a disruption to a sector affects other sectors. Even if you know what the aggregate effect is, it's quite important to understand whether the effect is affecting the shock is affecting consumption, final consumption, or it is affecting aggregate economic activity through disrupting other sectors. So that's one. Second, it's important for growth directly. And this is where, for example, Chetan, we talk about Bakai and Farhi, because they come out with this very interesting parameter, which is if you sum all these DOMAR weights, right? So DOMAR weight is sales by value added, or GDP, total value added. So if you sum all these shares across all sectors, you can imagine that this statistic will be greater than 1, because obviously the aggregate sale of a sector is composed of the value added, but also it goes in the intermediate production for other sectors. So since this statistic is greater than 1, they call it as input output multiplier, which basically implies that if you have a uniform productivity improvement across all sectors, then how much would growth increase because of that? So higher the input output multiplier, higher would be the growth, right? And essentially what we do, first of all, is we provide a closed form expression for extracting network spillovers of microeconomic shocks. So that hasn't been done before, and we are the first to do that. And second, we, in response to this second point, we illustrate empirically that variation in these input output multipliers for different countries at different points in time is mostly driven by network spillovers. So it's not the direct effect that actually dictates how input output multipliers are changing over time and across countries. It is network spillovers. It's how a shock to one sector propagates to the rest of the economy and then affects the economy instead of the direct effect. So that's one. The second application or motivation for this paper was to understand aggregate volatility, right? So you have different countries and they have different production networks, right? So the way all these 10, 100, 200 sectors are engaging with each other is different. And what we want to understand is how does this shape of production network affect aggregate volatility, right? So in this respect, what we do is we compute this fundamental volatility, and I'll explain more what I mean by fundamental volatility by this paper by Carvalho and Gebe for a bunch of countries. And then we compare it with volatility that emanates from a hypothetical sectoral production network of the US economy. And to break the suspense, what we find is that if you keep your final consumption expenditures same, so if you think about the case of India, if we keep consumption expenditure on all goods and services the same, and if we keep aggregate GDP the same, and the only thing we change is the way these 100 or 200 sectors engage with each other to produce those goods and services and make them the same as that of the US, we find that aggregate volatility in India would be much lower than what it is right now. And we find that for more countries as well. In fact, nearly 85% of the sample. And how we go about doing that is essentially the theoretical aspect of this paper. And finally, we have a more general motivation, and that is that you can evaluate the effect of changes or any changes in the production network to understand what is going to be the macro effect of microeconomic shocks, right? So I quite like this example because let's suppose that you have the automobile sector and it transitions completely or mostly to electric cars, which may happen sometime in the future. So the key question then is how, this will obviously change the network structure because automobile industry will now not, rely a lot on, say, petrol or oil, but rather on lithium-ion batteries and hence lithium production. So then the key question is how would a disruption, a microeconomic disruption to lithium production would affect macroeconomy? Probably it won't have affected the macroeconomy a lot 40 years back when you didn't have smartphones or electric cars, but now it would, or maybe in the future it would. So it's relevant for policy. And how can we evaluate the impact of the shock under this new network structure? So what's the challenge? The challenge is what you're saying is, let's assume that the automobile sector transitions to electric cars, right? So what you need is that in that scenario, in this counterfactual scenario where everybody has moved to electric cars, what would be the sales share of lithium industry, right? You need to know the DOMAR weight of the lithium industry. And the problem is that you don't observe the sales share of lithium industry in a counterfactual scenario, right? That's the key challenge. So in this paper, what we do is we provide a framework to analyze how specific input-output linkages contribute to aggregate fluctuations. And what we do is we provide a general approach that allows us to understand the macro effect of microshocks. And we can basically do that with any change. It's not just the network spillover or the volatility story that I've told you. It can be any change that you can think of. You can apply that to our formula. So we obviously give these two applications. We do the network spillovers that I'll talk more about, and we do this volatility application. Now coming to the literature. So here's the literature, and Chetan, here are all the papers of Bahal and Fari that you're talking about. And there's a big and growing literature on the production networks side. This is the theoretical bit, this is the empirical bit. In the theoretical side, you have essentially, as I said, the consensus is that microshocks affect aggregate output. But it's kind of broadly divided into two sets, where half of the literature is talking about how microshocks propagate in efficient economies. And then there's this second set of literature that talks about how microshocks affect the aggregate output, but with distortions or with markups or some other frictions and rigidities. And say, for example, this paper by Bahal and Fari, Beyond Haltom's Theorem, essentially talk about the fact that if you think about Cobb-Douglas production function, then Haltom's theorem is correct, right? Then the sales share captures everything. You don't need network. But if you think about, as soon as you move from Cobb-Douglas to, say, for example, constant elasticities production, then you have second order effects, and second order effects can be consequential. Now, where we fit in is that we're not really engaging with this literature on the inefficient production economy or second order effects. We keep our focus to the first order effects. But essentially what we're saying is that there is a lot within the first order effect that we're not clear about. We're not clear about what is the network spillover and what's the direct effect, even in the first order, and how do you calculate that? That is essentially where we are contributing. And in the empirical side, there are a lot of papers now that are now estimating how these shocks propagate through the network. And these papers by Barrett and Savignot and Carvalho et al., they use quasi experiments such as natural disasters to identify supply shocks, and then understanding how these supply shocks propagate through the network. And then there are a bunch of papers that extract shocks from the data and do the same thing and ultimately get to the same result. And our idea is more, again, extraction of shocks from the data, but again, trying to understand how you can, how can you quantify the network spillovers and the direct effect of these micro shocks. We're not going to the quasi-experimental literature. Okay, so the outline of the paper is as follows. After this broad introduction, we'll start with the Haltom's theorem, then we go to our CES model, and ultimately provide a non-parametric general statistic or formula that allows us to understand what is the importance of specific linkages in a production network. And then we apply that formula in these two applications, the network spillovers and the volatility application, and we'll conclude thereafter. Okay, so before I begin, are there any questions? I'll stop for questions, and then if there's none, then I'll go ahead. Nothing? Okay. So our starting point is Haltom, as I said. So this is essentially what Haltom says, that if you think about how microshocks will affect aggregate GDP, then it's summarized by the sales share, which we represent as lambda I, or the Domar weight, where Y is real GDP and D log AI is Higgs neutral productivity shock. And as I said before, this is a network irrelevance result. You don't need information about the input-output network to compute lambda I. So what we do is we characterize Domar weights or sales shares in the counterfactual economy in terms of observable objects. So we can compute the sales share in the counterfactual economy. That's the key contribution of the paper, that we give you a formula with which you can in fact estimate what sales shares will be like in a counterfactual economy. And you can do that using everything that you actually observe. And then we compare this counterfactual Domar weight with the actual Domar weight. If you aggregate all these sales shares in the actual economy and the counterfactual economy, that gives you the overall aggregate effect, or the difference in the effect of the network change, right? So assume that you kind of sever a bunch of links in the production network and you want to understand what's the aggregate effect. It's given by this resulting statistic Zeta, which is nothing but the difference in the input-output multiplier in the actual economy minus the input-output multiplier in the counterfactual economy. And the challenge usually is that you don't observe lambda I tilde, right? So let's get started with the CES model setup. We have a static competitive economy with n sectors. Each sector produces one distinct good. Sectoral output is consumed by the representative household as final demand, CI, or it can be consumed as intermediate input, XIJ. So XIJ would basically mean that sector I is using sector J's output in production. And producers use labor LI and intermediate inputs to produce. And we have two economies, actual and counterfactual. And every time you see a tilde over a variable, that essentially corresponds to a counterfactual economy, right? And you have this input-output matrix and labor share vector. So these are some definitions. Small omega essentially is a structural input-output matrix, right? It's not the observed, it's the structural input-output matrix where omega ij captures the importance of good J in I's production. So this is structural, you don't observe this. Similarly, mu I are labor share vectors, and they capture the importance of labor in sector I's production. Again, these are structural parameters and you don't observe them in reality. And obviously they satisfy the condition that all of these omega ij's and mu i's overall add to 1. Now, what's the difference, or what's the relation between omega and omega tilde? Because now we're getting to the, how do we get from the actual economy to the counterfactual economy? So each row of omega tilde can be expressed as a function of the corresponding row elements of omega, right? So if you think about omega tilde, it's a linear transformation of omega, right? Where you can write it as omega x, where x is an n by n matrix. And the key bit out here is that an element of omega I tilde is again a linear function of omega I in the original matrix, but their sums won't add to 1 necessarily because x can be anything, right? So if you add the importance of all intermediate goods in the counterfactual economy and you add the importance of intermediate goods in the actual economy, they won't be necessarily equal. What that means is that this will result in a change in the dependence in labor, right? But that doesn't affect our results simply because when you talk about the impact, the macro impact of micro shocks to these sectors, they only depend upon Domar weights and they don't depend upon mu's, right? But this is a caveat that's worth bearing in mind, that if you change the input-output matrix, you kind of have to make sure that this identity satisfies. So the reliance on labor would change. Okay, so what is real GDP? Real GDP is the maximizer of the CS aggregator, where these are consumption of CI is a consumption of good I, and AI is the importance that a representative household attaches to good I. So Moni, your question about where does the household fit in this whole system is that the household consumes goods produced by these n sectors in different weights. These are the weights, and CI is the consumption, the final consumption. Yeah, and sigma is the elasticity of substitution between different goods. Sorry, did you say that?
Yeah. No. Yeah. Thanks.
So Girish, 1 second. So there are multiple final goods sectors, is that right?
Yes. So there are N sectors. N sectors produce gross output. Gross output will be divided between intermediate inputs and final consumption.
And there's a network of intermediate goods.
Yes,
Okay.
exactly.
Okay. So
All right.
multiple heterogeneous sectors are interacting with a network of intermediate. It's
Yes.
like an intermediate trade network.
Exactly. Exactly.
Girish, one more question. Can you just go back? So your AIs, these AIs are all exogenous.
They're all exogenous.
Okay.
Yep.
Okay. Thanks.
So now what the household's problem is that it maximizes its log utility over aggregate consumption subject to the budget constraint, where W is nominal wage, L is labor, and you have PI, CI. So PI is the price of good CI. Both sides of this constraint, the left and the right, essentially are nominal GDP. This is the income accounting, and this is the expenditure accounting approach. Now let's get to producers. Producers produce goods I, and they're produced via the CES production function, where you have labor. We can have other factors of production as well, but we're just sticking with labor. It doesn't change anything. We can have more factors of production. And also a bunch of intermediate inputs. So Chetan, your question, this is essentially the overall production of the gross output of sector I. It uses labor, it uses intermediate inputs from all other sectors to produce the good. And obviously the counterfactual is pretty much the same, except you have different weights associated with these factors of production or intermediate inputs. And producer I maximizes profits in the following way. You have this profit, which is your total revenue minus your labor cost and your intermediate cost. In equilibrium, labor market's clear and your goods market clear as well. So for a particular sector I, you basically either produce good that gets consumed as final output, or your output is consumed as intermediate inputs by other sectors, right? Okay, so this looks ugly. I will, yeah, I'll say that. But it's important to define these, these IO matrices, because they're important from our perspective later down the line. So bear with me. Omega out here is the equilibrium input-output matrix. So this is different from small omega, which was the structural input-output matrix. Omega is simply the expenditure share of sector I on intermediate input from sector J as a share of its total sales, gross sales, right? And I'm not talking about counterfactual, but it means the same thing, but in the counterfactual economy. Leontief inverse would be, to those of you who already know about this, this is obvious, but for those of you who probably are seeing this for the first time, Leontief inverse would capture all direct and indirect exposures of a shock to I to J, say for example. So what's the difference between psi and omega? Omega would just capture the direct effect of a shock to, say for example, sector J to I. But when you talk about Leontief inverse, you can think of it in terms of the direct effect of a shock from J to I, but then also how J would affect I's customer, and then I's customer's customer, and so on and so forth. So it's basically everything put together is what Leontief inverse captures. This is the final expenditure shares, essentially highlighting the size of each sector in final consumption, right? So how much of electricity is consumed as final as a ratio of GDP, so to speak. That's final expenditure shares, and you have the labor expenditure shares as well, which is nothing but the cost of labor divided by gross revenue there, right? And from the goods market constraint that I showed you in the previous slides, we basically get to this equation. You have to believe me that this is correct, but essentially what we're saying is that these Domar weights or sales shares can be represented in network aspect like this. Okay, it's the final consumption expenditure shares into the Leontief inverse. And again, you don't need all of this in general. If you know sales share, you're done. You don't need all of this information. That's the beauty of Haltom's theorem. But I'll explain where our result or our framework starts incorporating these things. And as I said, lambda I is just the Domar weight, which captures everything. It captures the direct effect and it captures the indirect effect because you're having Leontief inverse and then you're kind of weighting it with the size of each sector. Okay, so let's get back to the central problem. The central problem is that, as I said, lambda I tilde is unknown. So because of that, the aggregate relevance of these changes that you've made in the counterfactual economy is also unknown. When you're doing these differences in the input-output multipliers, you don't know what they are because you don't know what lambda tilde is. So we make two assumptions to help pinpoint what lambda tilde I is. So what are the two assumptions? First assumption is that consumption weights, when you define the household's consumption function, they are equal in the observed and counterfactual economy. What does that mean? That means that if you spend, if for you, milk is important, and you spend 1,000 rupees on milk every month, in the counterfactual economy, it'll remain the same, right? It'll have the same weight to your consumption. And we also assume steady state. So whatever we are talking about, our comparisons of the difference in input-output multipliers will happen in steady state. So all your Hicks neutral productivity parameters are basically equal and equal to 1. And I'll explain why, what these assumptions do once we solve our model. I'll stop for a bit if there are any questions. No? Okay. So this is where we are solving the whole model now. So I won't take you through the algebra. Again, you just have to believe me that these equations are correct. But essentially, when you solve the household optimization problem, you get expression for what the final consumption for industry I is like. And it looks like this, where capital P is the price index. You have the first order conditions with respect to labor and intermediate. So you also understand what's the labor demand for industry I, and you know what's the intermediate demand of industry I from sector J, right? And if you plug these equations into I's production function that I showed you initially, you get this price equation, okay? Now, using these expressions for Xij, Li, and Ci, we get these three equations, right? Where all we're kind of expressing is what omega ij, which is the observed equilibrium expenditure shares that you actually observe in the economy, what is it equal to in terms of the structural parameter and a bunch of other parameters. Similarly, this is the observed labor shares, and how is it related to the structural importance of labor in production and a bunch of other parameters. And this is how BI, or the final consumption expenditure, is related to your preference parameter in the consumption function, okay? And this is where we use our two assumptions to solve our, or to get to the idea of lambda tilde, or the idea of computing Domar weights using observable parameters. So what does assumption 1 do? What's the contribution of assumption 1? So what assumption 1 ensures is, because we are assuming that consumption weights are equal in the actual and counterfactual economy, we essentially ensure that when this input-output matrix is changing, final consumption shares are not changing, they're the same. The only thing that is changing is the actual matrix, the input-output matrix. That is where the difference in lambda would come from. It won't come from changes in final consumption expenditure. It'll only come from the fact that this production structure has changed, right? And together with assumption 2, which I'll discuss in the next slide, we ensure that the initial level of GDP is same. And I'll show you and show that to you in the next slide how that happens. But again, this is very important, right? So if you think about what I discussed earlier, the idea that automobile sector transitions to electric cars, when you're making the comparison of how micro shocks will affect aggregate output, you need to keep the level of GDP in both economies the same, because if the level of GDP itself changes, then the comparison is meaningless. So that is why our assumptions wanted to ensure that real GDP is the same. The only thing that changes is the production network, and then we can understand how micro shocks will affect this initial same level of GDP. So now let me explain what's the relevance of assumption 2, where we said that we are talking about steady state, where Hicks neutral productivity parameters are all equal. So the steady state essentially ensures that all, the prices are the same. So all prices for all sectors converge to the same parameter. And that is why you simplify. AI is obviously equal to 1 as I assumed, and these parameters cancel out. It also results in the fact that prices are equal to wage. The price of sectorized output is the same as wage. And this is obviously a direct result of the fact that we are working in efficient economies. If you start talking about inefficient economies, then you start having terms like mu, etc., which complicates things a lot more. But this is, so again, these parameters cancel out. And then you have this BI, which is the final consumption expenditure share, and that simply boils down to AI. So if you focus on these equations, you get some very important result. What you find is that under these two assumptions, your observable omega or your observable expenditure shares are equal to the structural parameters. That's the key result. As soon as you get this, you can do anything that you want. This basically allows you to compute lambda tildes, and I'll show you how. And together with assumption 1, your initial
Girish, I have a question here. You didn't say anything about this relationship between thetas and other parameter. What is there? Sigmas. Are they the same?
No, they're not. So theta would be the elasticity of substitution in the production function, and sigma would be the elasticity of substitution in the consumption function.
No, I'm saying when you compare with the counterfactuals.
Oh, so they are the same. You can assume them to be different.
Girish, but remember, so there's no difference. So we can assume them to be different in the counterfactual economy, but it doesn't make a difference to the result. So
okay.
You can assume them to be different, but it doesn't make any difference exactly. So where was I? Yeah. So yeah. So ultimately, what you get is your real GDP and the counterfactual GDP both boil down to 1. So they're the same. The initial level of GDP is the same. That allows meaningful comparison. So what's the proposition? The proposition is, if you recall the original form where we said that zeta is basically the difference of input-output multipliers, and this can be again represented like this, right? The vector B into Leontief inverses of the real and the counterfactual economy. And the key result that we're getting is that if you do any kind of linear transformation to this structural omega matrix, whatever that transformation is, you can express zeta as essentially this term would become I minus T omega. You apply the same transformation to the observed expenditure shares, the observed input-output expenditure shares matrix. That's it. So whatever you're thinking about, whatever your X matrix is up above, out here, whatever your matrix is, whatever kind of transformation you want to apply, all you need to do is you need to apply the same transformation to the observed parameters, the observed matrix. You don't need sigmas or thetas. So Moni, to your question, that's the beauty. You don't need elasticities of substitution in the real and the counterfactual economy. They are irrelevant. And that's
that's
key.
interesting.
Yeah.
Yeah. Okay, thanks.
And so that's it. So that's the theory. So if you're with me till this point, we're done. And now what we can do is we can use this result to.
So is this, Girish, I'm sorry. So is this because of the specification of the functions? I mean, yi and yi tilde, and
what do you mean?
Well, I understand that you do not need sigma and theta given your algebra, but what is the intuition behind it? I didn't get it.
So, I mean, if you think about Cobb-Douglas, for example, that's a specific case of CES. But if you think about CES, I think the key bit is that are these two assumptions, assumption 1 and 2, because ultimately these parameters that you're seeing here, where thetas ultimately do matter because they're coming in the equation, they cancel out.
Right.
I mean, you have thetas and sigmas out here, but they cancel out under the assumption that you're talking about steady state, where Higgs neutral productivity parameters are equal. That's all we are assuming. Beyond steady state, obviously things will be a bit different, but yeah. I don't think the literature is working on beyond steady state. I think most of the papers I see are on steady state.
Okay, thank you.
But yeah, your point is interesting. Right? If you start thinking about deviations from steady state, then you have these parameters, and then you have to think about some ways to be able to, it's a good point. If you have deviations from steady state, then you need thetas, then you need sigmas, and then it's challenging. It's challenging, to be honest, because then you can't apply the same transformation as easily as you can out here.
Thanks.
Sure. So now we get to the empirical applications, right? So with this formula, we can explain everything that we wanted to explain in terms of network spillovers and volatility. So what we do, first of all, is we want to understand how fluctuations in network spillovers are associated with fluctuations in GDP growth rate. And maybe this network spillover application will clarify more about exactly what we are doing. And then we get to volatility application, where we ask, what would volatility be if the network structure of a country would be the same as the US's? And what we find is it's lower for nearly all countries in the sample. And for this, we use data from World Input-Output Database for 43 countries. And we also use Penn World Tables for GDP and total factor productivity series together with other controls. Okay, so let's get to the first application of network spillovers, right? So as I said, this is the input-output multiplier as used by Bahal and Farhi. And the idea is that for an increase in total factor productivity, uniform increase in total factor productivity for all sectors, a higher input-output multiplier would lead to higher rate of economic growth. So we just test that. That's straightforward in the sense that we're not saying something new. This is already explained by Bahal and Farhi, and we just test that. And we find that is in fact true. So we just do a simple regression of GDP growth on input-output multipliers, total factor productivity, the growth of total factor productivity, and a bunch of other controls. And what we find is, if you just focus your attention on the last column, because that's the most relevant with all controls, and with all controls, what you find is that input-output multipliers are in fact very significantly contributing to GDP growth. Now, what's the interpretation of this coefficient? The interpretation is that if you have a 1 standard deviation increase in input-output multiplier, that is associated with approximately 0.8 percentage point increase in economic growth rate. And these results are robust to inclusion of lags of real GDP growth and total factor productivity growth, etc. So this result is obvious because this is kind of also shown by Bahal and Fari, and that's not surprising. Input-output multipliers are important for growth. Where we come in is we kind of explain, okay, so remember this now, that total factor productivity, input-output multipliers are important for growth. What we do is we first of all explain how we calculate network spillovers, and then we explain how they matter for input-output multipliers, right? That's the exercise. That's the first application. So first of all, how do we define network spillovers? So it's the effect of shocks on final demand due to indirect propagation through other sectors. So you're kind of purging out the direct effect of macroeconomic shocks on GDP. You're looking at how a shock to, I don't know, electricity sector would affect aggregate GDP through disrupting other sectors, but not directly through the value added by GDP sector, if that makes sense. And how do we do that? So this is the graphical representation of what we are about to do. So this is, so Moni, you asked the question, I was referring to this figure initially. So this is the, the economy that we visualize, the actual economy. You have factors of production. We assume factors of production to be limited to labor, but you can assume other things as well. You have N sectors, and you have the final household, the representative household that consumes final consumption goods from these sectors. And the way this economy functions is that every sector takes factors of production to produce, but also it relies on other sectors, intermediate inputs, and sometimes by, it relies on intermediate inputs by itself to produce whatever it produces. And then basically other sectors consume their output, and then household consumes final consumption. So what we are doing in this network spillover story is we are saying, okay, so if you want to understand the direct effect, if you want to purge out the direct effect, you have to assume a counterfactual economy where there are no links, right? So there are no intersectoral trades happening. You have factors of production. Sectors can rely on themselves, their own output, but they cannot rely on each other to produce, and household will consume the final output. And what happens in this economy? And then we can compare and we can purge out the direct effect to understand what is the network spillover effect. So for this, as you can imagine, what we are going to do is we are going to define omega tilde in this specific case as diagonal matrix of the actual economy, right? Because in this economy, the only thing that we are allowing is that the production function for sector I can use labor and intermediate input produced by its own self, the sector I itself. It's not using J, K, L, M, blah, blah, blah. That summation is gone now. So it's only using labor and intermediate input by its own sector. And you have the profit and the market clearing conditions as the same. That's it. So this is the application where we are defining exactly what omega tilde can be. And this is the implicit assumption. Again, I did discuss that initially as well, and it's worth going over it again, that the sector's dependence on labor in this case would increase necessarily in the counterfactual economy, precisely because mu I tilde, which is the importance of labor in this counterfactual economy, needs to satisfy this condition. But again, it doesn't matter because network spillovers, zeta, that we are going to measure now, does not depend upon mu I tildes, right? Because we are only considering productivity shocks. If we were to consider shocks to factors of production, then they'll matter. Okay, so the network spillover story is as follows. You have zeta as this. You have the B vector, which is the final consumption expenditure share for all the sectors. You have the psi, or the Leontief inverse, again, that you observe, because you observe the expenditure shares, the input-output expenditure shares, and then you observe psi tilde as well. In this case, psi tilde is I minus diagonal omega. And do you see where this is coming from? This is coming exactly from our result. This. We apply the same transformation to the observed input-output matrix, right? That's it. That's the result. So because of that, we can compute Zeta network, right? And again, so if I explain this specifically for one particular element, because this is the aggregate, right? So you have double summations, you're summing over i's and you're summing over j's. So if I give you a more specific example, maybe that'll clarify exactly what is happening. So let's talk about the effect of the network effect of a shock or a disruption to electricity sector, right? So you have this expression. So what does lambda JE imply? Lambda JE represents how a shock to electricity sector would affect final consumption of good J that sector J produces, right? Lambda EE would encompass two things. So lambda EE would be obviously the effect of how, you know, a shock to electricity sector affects the final consumption of electricity. But the point is, it's a little complicated because this lambda EE encompasses two things. It encompasses the direct effect to household, but it also encompasses feedback effects. So you can imagine it like this, that if there's a shock to electricity sector, it will obviously affect direct consumption of electricity, but then it may affect the production of solar panels, right? Because solar panels may be produced using electricity, right? So now if you are not being able to produce solar panels, what's happening is that, again, it'll have a feedback effect on the production of electricity itself, right? So the sector will get affected again over many iterations by affecting other sectors as well. And all these feedback effects are network effects. So what we have to do is this, lambda EE that encompasses both direct and feedback effect. We have to purge out the direct effect to get the importance of the network spillover. And this B psi tilde represents only the direct effect of the shock to E on final consumption. Why is that? Because in this economy, in this counterfactual economy, there is no scope for feedback effects. You just have a diagonal matrix, and a shock to the electricity sector can only affect final consumption for electricity. It cannot affect any other sector. So that is why we kind of purge this out. So if you look at this equation, it's not very intuitive, but if you solve this further, you ultimately get this point, right? So these are obviously all network effects, because this is how electricity sector disrupts other sectors. But then even within lambda EE, you have direct and feedback effects, and you want to keep feedback effects, and you want to kind of purge out the direct effects. So this is what you get. And this is how we calculate Zeta network. Now to the relevance of Zeta network. So again, the explanation is that Zeta network captures the total indirect exposures from all sectors to final demand. And it's related to the input-output multiplier in the following way. It's pretty intuitive. The input-output multiplier, Xi, is equal to Zeta network plus the direct component. That's it. So because we know now what the Zeta network is, we can simply subtract it from Xi to get the direct component as well. And what do we do with it? We run a very simple regression. We regress the input-output multiplier that I discussed about from Bahal and Farhi, and we regress it on network spillovers and direct effects. This is not really relevant. What is relevant is that network spillovers explain most of the variation in input-output multipliers. That's the most important result. Graphically, if you see, for most of the countries where the blue line is the input-output multiplier, and it shows how the input-output multiplier has evolved over time. And you can see for most of the countries, it's more than one. It's close to two rather in most of the countries. And what we see is that this multiplier is closely tracked by network spillovers for just about every country and across the time sample as well. So that kind of, it's a very interesting result that network spillovers matter this much in explaining input-output multipliers and consequentially growth. And the interesting thing is that you can create these network spillovers through this formula. So is there any question before I move on to the second application? Is there any question on the network spillover story? Because that is kind of, I hope that clarifies the application of the theory, the more general theory. No? Okay.
I'm still wondering what you're picking up here. Could be that across the network there are positive spillovers, but there could be negative spillovers too, right? So these are like average effects, but why could be that the negative effects from network spillovers cancel out with the positive effects, although your regression is picking up average effects. So is that the right way to think about it, or
that's a brilliant point. Yeah, that's a fantastic point. That's exactly what it is. When you think about, if I go back to this aspect, Leontief inverse, right? I have to go back. Yeah, out here. So when you look at the Leontief inverse, when you think about a shock to J and you're thinking about how it affects I directly, it can be one thing, it can be negative. But then if you think about how J affects I's customers and hence it affects sector I, it can be different, it can be positive. And then you have the effect emanating from 2 path lengths and then 3 path lengths and, I's customers, and so on and so forth. So you can have, very different effects of a microeconomic shock to a sector. And what we are capturing in the network spillover, you're very correct, is the aggregate effect. It's basically the sum total of any positive, any negative effect that you can have. But the interesting thing is that we weren't even able to do that up till now, right? Up till now, the idea was that you have a shock and you can understand what the aggregate effect is, but you have no way of understanding what is the network spillover effect, whether it's, as you say, some of the interactions can be positive. That's a good point, actually. And some of the interactions are negative. That's even deeper, and it'll be great to actually delve deeper into that. But we have no idea of understanding what's the aggregate spillover story. And this exercise kind of helps us do that. But I agree with you, it's an aggregate.
And one other question. So since you're dealing with intermediate good networks, can you say something about market structure and in intermediate good trade and the impact on, on negative spillovers, positive spillovers? Presumably you could, right? Because
you can do anything. You can. That's the interesting thing. I mean, we are thinking about another paper that talks about how downstream linkages matter, how upstream linkages matter. So the beautiful thing is, if you think about the formula, the zeta that we are constructing, you can apply any transformation that you think is important. You can, if you want to see how specific, intermediate linkages to say oil or any other sector matter for the aggregate economy, you can sever those links with the appropriate linear transformation, and you can study the aggregate effect.
Yeah, but what I'm asking is, I mean, don't do the self-sufficient and the full network comparison, but do the monopolistic competition and perfect competition comparison, right? Because you would know what networks are, imperfectly competitive. What types of networks have what type of market structure? I mean, so there's a lot going on there. I mean, they're offsetting negative, positive spillovers, but there's also across all these countries, there are different market structures for different intermediate good networks. So, so I'm wondering, if you don't control for that, if you don't control for these fixed effects, so to speak, what, are you, I mean, can you really put these graphs up together and, and say that the network spillovers are driving the input-output multipliers? Because you're not controlling for other things that could, drive the input-output multiplier.
No, so analytically, input-output multiplier would necessarily be, just analytically, you don't have to worry about anything else. Analytically, input-output multiplier would necessarily be equal to the network spillovers that we have calculated and direct component. And network spillovers in themselves, I completely agree, are an aggregate as well. They are. But the point that we are making here is that whatever that aggregate is, which we were not able to measure at this point, are extremely important in dictating fluctuations in input-output multipliers. It'll definitely be very interesting to dissect input-output multipliers and understand the interactions that you're talking about. But analytically, I mean, this is not, you don't have to control for anything else. This is analytically true. Input-output multipliers are in fact equal to network spillovers and direct component. And then you ask how important network spillovers are as aggregate. But your point about what's the relevance of production structure itself is exactly what actually the second application is about. Because there, what we are saying is we keep everything else fixed. We keep final consumption expenditures fixed. And then we change the network structure. And then we ask, how does aggregate volatility change then? So I'm coming exactly to that. What happens when you just change the network and keep everything else constant? Does that kind of answer your question?
Yeah, except when you're doing that exercise and when you're just saying you're changing the network, what's embedded in that is a particular market structure. So, so you seem to be interpreting that as when you change the network, that means more linkages across sectors, but it could be that the market structure across two networks, which are equally linked, are different.
Yeah, it's possible, and we
So,
don't do.
So when you say that you're picking up the network effect, it's not clear to me that's a clean. It seems like it's still a noisy indicator of these network spillovers.
So let me put it this way. Our comparison.
Maybe I'm not understanding it, but that's
yeah, no, that's fine. But let me put it this way. Our comparison is necessarily linked or based on efficient networks. We are not. I completely agree with you that the networks, the market structure itself can be different in the two countries, and we do not control for that at all. We necessarily are not going into monopolistic competitions or distortions or inefficient economies, because then you don't get. Then you start dealing with second order effects, etc. And we're not getting there. It's not that it's not important. All I'm saying is, up till now, you were not able to calculate network spillovers even to the first order effect. You can definitely include second order effects and they're consequential. But my point is, up till now, you didn't even know what the first order effect was composed of. So when I'm making these comparisons, I am assuming perfect competition and efficient economies, no matter whether I'm comparing India with US or anything else. And if you ask me, it's a big assumption. Yes, it is. But the point is that allows us to do something that we simply couldn't do even for first orders.
Yeah, I mean, sorry, I don't want to take up too much time, but you have an elasticity of substitution, so presumably you can calculate the markups. But if you are, if you're saying that you're imposing perfect competition, then I guess price equals marginal cost. And but if you write down a CS production function, I would think you could say something about market structure, but
you can. Maybe
I'm not understanding it. But
no, I see your point, and maybe we can do something about it as well. It's just going to be, I mean, I foresee it to be analytically challenging, because what you're bringing out is that some structures can be inefficient, and then you have to also have the knowledge of which structures or which interactions have distortions. Although there is this paper by Ernest Liu that says that you don't have to worry about distortions at sectoral interaction level. You just have to think about distortion centrality, as all distortions kind of become bigger at upstream sectors. So you can think about those things as well. And we have necessarily kind of not taken that route, but you can. I think that's a good point. One can think about it and say what you can, if market structures in terms of competitiveness are different as well.
Yeah.
Okay, so let's get to the aggregate volatility story. So this bit is all about. I have what, Ganesh, how many minutes do I have now? 5, 7?
Yeah, you got about 10 minutes.
Okay, great. So I'll try to wrap up in 10 minutes. I think I should be able to. Okay. So the second application is about how do input-output networks contribute to aggregate volatility. And again, this is assuming efficient networks and efficient economies. You're not thinking about distortions or markups, although you can, technically speaking. So the idea is how you compute aggregate volatility if you keep everything else constant. You keep the final consumption expenditures constant. If you're talking about India, you keep final consumption expenditures the same. You keep the level of the GDP same. So preferences over final goods don't change. Level of GDP does not change. The only thing that changes is that you rewire the intersectoral operations in such a way that they produce the same goods in different ways, in ways exactly similar to the US. That's it. So you're just changing the recipe with which products are produced, but the preferences over those products are the same. The level of the GDP remains the same. And you just want to understand how aggregate volatility would change. So again, the starting point here is Haltom's theorem, and basically says that changes in aggregate GDP for country C at time t is essentially equal to the weighted sum of productivity changes in industry I, where weights are the industry I's sales share, right? That's it. That's nothing new. Haltom said that in 1978. And what we do is we construct TFP series using gross output and value added data from WIOD. And we take the variance of this expression, where delta log AI CT is simply represented as A cap for convenience. So what we are doing here is we are taking the variance of this expression, and essentially this bit gets, the covariance term gets cancelled simply because we are dealing with idiosyncratic shocks, idiosyncratic sectoral shocks. So we are assuming that they are random and they're not related to each other. You can assume things to be not random, but that would only help our story in the sense that what we're trying to explain is how uncorrelated idiosyncratic microeconomic shocks can matter to aggregate volatility. So when you start thinking about correlated shocks, then obviously they can matter more. So this is a more stronger assumption, or rather a weaker assumption. And we compute standard deviation with this expression, with just the first expression, where variance of AICT is basically variance of the whole time series, and hence it's time invariant. And the key bit is that your variation in sigma y, which is the aggregate volatility, comes from movements in Domar weights. That's basically what Gebe and Carvalho call as fundamental volatility. So what they're saying is that if you track the volatility of US growth rate, it's mostly explained by this fundamental volatility that's coming from Domar weights, or changes in Domar weights, right? And now, because of what we have done earlier, if you want to understand counterfactual volatility, the only thing that you need to do is again assume that your small omega is the same as omega for US, which basically means that your capital omega, or observed equilibrium matrix, is the same as the US, and essentially you get your lambdas to be the same as the United States input-output matrix. They're calculated using input-output matrix of the US. And then you can calculate the aggregate volatility that you get from the counterfactual as opposed to the real. That's it. So this is again, the result is coming from our initial formula that basically says that the only thing that you need to change is with the same transformation is the actual omega, which is the observed input output expenditure entries. And this is what we find. On the y-axis, you have percentage change in volatility. And on the x-axis, you have a bunch of these countries that compare how aggregate volatility would change if their consumption or final consumption expenditures were to remain the same, but their production network was exactly the same as the US is. So US is, that is why US is at 0, because it's the baseline. And what you find is that nearly 85% of the sample is becoming less volatile if the production network is the same as the US. Now, again, this comes with the caveat, as Chetan mentioned, this comes with a caveat that we are assuming perfectly competitive production structures in all the economies. If you were to include distortions, I'm pretty sure we're going to find very interesting results. Maybe that's going to be a second paper. But this is essentially what we're finding, a very interesting thing, that by only changing the network structure, but keeping everything else constant, you can significantly reduce volatility. In fact, you reduce volatility by 7.5% at the mean. The median is 5.8. But for some of the countries like China, Australia, Russia, and India, you see aggregate volatility decreasing in double digits. So it's very consequential. And that's it. I'll stop now. So essentially, that's the conclusion, where we provide a theoretical framework to analyze how any arbitrary set of input-output linkage can contribute to aggregate fluctuations, or what's the relevance of specific input-output linkages. And the most important point of the paper is that you only need observed final expenditure shares, nominal sectoral gross output, and bilateral intermediate good sales to actually calculate these this formula. And we provide two applications. One is a network spillover story, and the other is fundamental volatility. But you can ask many different questions based on whatever you think is an important application to this theory. You can basically see for any links and then understand how consequential or important they are. So I'll stop there, and it'd be great to get some comments.
Thanks, Girish. So we have about another maybe 10 minutes in which we can take questions. There's already been quite a few, so I want to thank all the participants for their questions. But we can open it up for more general questions now. Girish, I actually have one question. So just on that last slide that you showed with the figures, do you have, I mean, I'm not a specialist here at all, so I don't have any intuition on this. But China and TWN is what, is it Taiwan? Is it?
I think so. It's Taiwan.
So there's a pretty major difference between the two, right?
Yep. Where is Taiwan? Wait a minute. Where is Taiwan?
It's right.
Oh, yeah, out here.
Yep.
Yep.
It's almost zero. That kind of caught my eye a little bit. Anyway, I just thought that was an interesting observation.
Yeah, no, it is. And again, what we are able to find here is that changing the production structure itself is very consequential. What we are not able to explain is why. I mean, that'll be very interesting to further investigate. Why do you see this? Obviously, this has got to do with the size of the input-output multiplier, which is very clear because the size of the US's input-output multiplier is low, and as a consequence, you have this result. But it'll be good to understand exactly what is going on that is driving this result.
So, any other questions? Okay, so it doesn't look like we have. So we can end the seminar here. So thanks again to our speaker and to
Thanks,
everyone
Girish.
else.
Yeah.
Thank you.
Thank you,
Thank
Girish.
you.
Very nice talk. Yeah.
Thanks for all the comments, Moni and Chetan. I think they're definitely helpful, and I mean I agree with the market structure thing that you're talking about. Yeah, excellent. Thank you.
Thank you. Yeah. Take care.
Take care. Bye.
Bye.
All right, Girish. Bye. Thanks.